Before I start, I want to thank the organizers for putting together such a great week. And I know for me, a lot of new projects have been seeded here, including, we see a new project being seeded right before our eyes, right? So thank you to Riddhi and Arvind and Manju, and let's give them all a... I thought I'd end by telling you what I talked about in Mumbai on Wednesday. But I don't have to start from zero here because you already know the basics, so I'll take advantage of that knowledge to go a little further than I could in Mumbai. So I chose the title Circles in the Sand as a kind of reference to a story about Archimedes that, back in the day, they used to do geometry on the beach. It was kind of their version of a blackboard. So he would go to the beach and he would, draw lines and circles and do his calculations there. And the story, which I guess historians pretty much don't believe is actually true, but the story is that the way Archimedes died is that he was doing geometry on the beach one day when some Roman soldiers arrived and were kind of storming up the beach, invading. And Archimedes was very annoyed that they were, messing up his circles. They're kind of messing up his beautiful diagram. And so he started lecturing them, "Don't disturb my circles." And those were his last words. So this is joint work with Wes Pegden and Charlie Smart. Okay. You all know the Abelian sandpile by now. So this is the deterministic topplings in ZD to their 2D nearest neighbors. And here's an example of stabilizing a little pile of 16 chips, but of course in Z2, but of course we can stabilize big piles, and we have an Abelian property. And here's what a moderately big pile looks like. So this is a bitmap image. There are 4 colors in the image, and each pixel is colored according to how many chips ended up at that vertex of Z2, where the starting configuration was 1 million chips here in the center. And, well, many people have thought to make this picture, right? It's like a kind of natural experiment to do. So, as far as I know, the published mention of it was Ostojic. But maybe people did these experiments even back in the 90s, I don't know. I'm sure Deepak, actually Ostojic was Deepak's student, right? So anyway, many people have made these images and amazed by them. And there was a breakthrough in 2011 when Pegden and Smart proved existence of a limit shape. So you take n to infinity, rescale your picture so that it has area 1. We know that there's a limiting shape. It's still open to determine what the shape is. Okay, I'll skip the next couple slides. There are other experiments you can do in the sandpile universe. And there's a lot to say about them, but let's stick to this n chips at the origin. To enlarge the family of experiments a little bit, you could start with some background chips. So you have n chips at the origin, but maybe you have a background of h, okay? And the simplest form of h is that it's a constant, okay? So h equals 0 is this picture that we have already seen. You could take h equals 1 chip at every side of Z2, and then start your n chips at the origin and stabilize. And you get this thing that looks pretty close to an octagon, although it has some rounding at the corners. And h equals 2, something nice pops out. You get a perfect square. So the set of sites that topple is exactly a square in Z2. That was discovered and proved by Fay and Reddig. And, well, it's nice to have that example because at least in that case, we have a very simple limit shape which we can actually prove. Of course, the structure on the inside is much harder and more interesting. It's nice to know the exact shape. And then you can try other backgrounds, okay? You could try h equals 3, but you soon discover that that's too much. So if you drop one chip on a background of 3s, it's going to set off an infinite avalanche and never stop toppling. So you've seen this dichotomy that any sandpile is either stabilizing or exploding. Yes. Yes. So if you start in ZD, if you start with 2 less than the degree, so 2D minus 2, chips background everywhere, and then you drop n chips at the origin, you will get a cube. With an empty background, then we don't know the limit shape, even in 2 dimensions. So, yes. So the Pegden-Smart theorem, yeah. If you just want existence, then we know it in all dimensions. Yeah. It's just we usually don't know what it is, except for these special situations. Yeah. Background of 2D minus 2 in D dimensions in ZD, and then you start n chips at the origin, you'll get a cube. That's proof. That's Fay and Reddig. So, one thing you could try to do, given this dichotomy that we've seen, is classify backgrounds. So, some backgrounds will be stable, but if you perturb them by just adding 1 chip or 10 chips or some finite number of chips, they will become exploding. Right? And you can do that with deterministic backgrounds, and you can also ask these questions for random initial configurations of sand. So this is my currently favorite open problem to highlight because it's so simple to state. So suppose you start a IID random sandpile in Z2. Okay, so pick your favorite discrete probability distribution, mu. So say mu is supported on negative integers. And you can even, if you want to keep things finite, you could say mu is supported on integers between 0 and 10. Okay? And then use that distribution to make an IID sandpile in Z2. So every vertex has a random number of chips with distribution mu, and those random numbers are all independent. So that gives you a sandpile, and then you can ask, is that sandpile stabilizing or exploding? And all I want, it doesn't sound like much, all I want is an algorithm. I don't care how long it takes, just an algorithm to decide which. So for example, related to the threshold state that I talked about earlier in the week, find the smallest real number lambda such that the IID Poisson lambda sandpile on Z2 is exploding. That's this. So the lambda mentioned in the second line there is this value you might remember from earlier in the week, 2.125288. So, this value is something we estimated with, from big numerical experiments, but, we don't know how to, we don't have some like infinite series or something that has this value. We don't really know conceptually what it is. Okay. Something that, well, I guess I didn't exactly say this fact, so I won't skip it. So proving an explosion is easier than you think. You don't have to do all the work of proving that every site topples infinitely often. It's enough to prove every site topples at least once. And, well, the slickest proof of that is the least action principle, right? So if every site topples at least once, you just subtract 1 from the odometer, and you'll get a smaller odometer. if you want to prove it from first principles, you can give a contradiction proof, as shown on this slide. Okay, we have an odometer function, and as we saw yesterday, so the odometer is defined as the number of times x topples, and the Laplacian of the odometer tells you the net change in chips. So it gives you the final stable configuration minus the initial thing you started with. Okay, and this leads you to least action principle. So, so one way to characterize the odometer is the pointwise smallest integer-valued function v that is non-negative and stabilizes what you started with. So you could ask, maybe Z2 is an ambitious graph, and you should look for kind of simpler toy examples where you can actually analytically compute this lambda. And yeah, we have a few very simple sort of one-dimensional graphs where we know lambda. Actually, to me, the most instructive one is, so Anna Fey came up with the names of these graphs. She called this the bracelet graph. So it's just Z with doubled edges. And in a way, you would think sandpile is not very interesting on this graph because you could just reduce it to sandpile on Z. So it has degree 4, two edges on the left, 2 edges on the right, and 4 chips topple, 2 to the left and 2 to the right. So that's the toppling rule. And, well, what that means is all the chips always topple in pairs, and so if you have odd chip values, the odd extra chip just never moves. So the dynamics just reduce to sandpile on Z, which is easy to analyze. But then for this question of stabilizing an IID, it becomes a tiny bit non-trivial because, for example, a Poisson lambda has a certain probability to be odd and a certain probability to be even, which depends on lambda. And so the number of kind of wasted chips in your initial distribution depends on lambda. And so this graph, it's easy enough that you can, using the fact that that the critical mean for Z is 1, you can then solve for the critical mean for Poisson. And you get that it's the unique fixed point of some function with an an e to the minus lambda term and a lambda term. So it's some, there's a very explicit description of it, right? But it's already, at least a tiny bit interesting. So I don't know. I think this is a good. It illuminates something that, somehow the reason for the difficulty of this problem is that some chips are wasted. And here it's easy to see which ones are wasted. But on a more complicated graph, it's hard to detect which ones are wasted. Okay. If you take the least action principle and mess around with it, you can put it in a more convenient form. And that form ends up looking like this. You take capital G is the green function of ZD, and we're going to use minus the green function, or minus n times the green function as an obstacle for an obstacle problem. So we're looking for, the problem asks for a function w that's pointwise larger than minus n times the green function, and its Laplacian is upper bounded, so it can't kind of bend up too fast. And so this is the classical kind of obstacle problem, and then this last condition is, what introduces the difficulty that, the difference between the obstacle and the solution W has to be integer valued. Okay, and so as I alluded to yesterday, as a first approximation to these problems, you should replace integers by reals and see what happens. And this is the slide I mentioned yesterday that illustrates the difference. So here you have the Abelian sandpile from n chips at the origin with all of its patterns and its non-circularity. And here you have replacing integers by reals, you get divisible sandpile with its close to perfect circularity and no patterns. Let me state for you the Pegden-Smart theorem about the scaling limit of the sandpile. So you can write the sandpile of n chips at the origin as, well, here's the n chips you started with, and then you're going to add Laplacian of the odometer. And we're going to ask for limits of two things, the sandpile final configuration and the odometer. And the scaling for the sandpile is the obvious thing you would guess. So there are n chips, and you expect them to fill up a volume of order n, and so you should rescale each dimension by the dth root of n. So that's this Sn bar, is the rescaled sandpile. The scaling for the odometer is, well, there's a couple pieces. So you're going to rescale space by this same factor of r, which is the dth root of n. And then the odometer is blowing up at the origin because that's where the chip started. So it's kind of useful to subtract out that term because what you're left with is smoother and nicer to work with. So and when you subtract out that term, the rest of it has, because it has bounded discrete Laplacian, it is, it grows quadratically. So it's, for example, on these periodic patches of sand, what you find is it exactly equals a quadratic function plus a periodic function. So that quadraticness is what, that's why you want to use r to the minus 2 on the outside. So and there are other ways to see it, but okay. So you have these rescaled things, and what Pegden and Smart showed is they have limits in appropriate senses, and let me focus on the limit of the sandpile itself. So that's a weak star limit, meaning it doesn't capture very small scale details of the sandpile. It captures local average density. Okay? So it's a convergence of local averages. So it means, near any point in RD, you can ask, well, when I make the lattice really, really fine, what's the amount of sand I see in a little ball centered? That's the kind of behavior that this limit S is capturing. So it's not everything you would want, but it's a really good starting point. So intuitively, what is this theorem saying? It's saying, why these two pictures look so similar, even though, this picture lives on a different lattice from that picture. Because this picture, since I started with more sand, I had to rescale the whole thing by a factor of root 2 to make them the same size. And so the lattice size is, the squares in this lattice are, you have half the area of the squares in that lattice. So they're incommensurable lattices. So I can't really match these pictures up pixel for pixel. Yet, if you stand back from where you're sitting, they look very similar. So that's what the theorem is explaining. And what it's missing is all of this fine periodic structure. So when you zoom in on the sandpile, you see these distinct patches where, here's a patch of blue which indicates 3. So every site of Z2 in this particular region ended up with exactly 3 chips. And over here you see some periodic pattern of blue and red, which is 3 and 0. So there's periodic pattern of 3s and 0s. And then there's this periodic pattern in the middle here. And when you take the weak star limit, you won't see those patterns, you just see the average value of the pattern. Now, what's really cool about their method is it lets you take the integrality constraint all the way to the limit and kind of keeps track of it. And the way that they keep track of the integrality, it ends up being encoded in this object gamma. So gamma is a certain set of symmetric real d by d matrices. And you can think of it's kind of encoding sandpile dynamics after you've passed to the limit. So you can't do topplings anymore in RD, because your lattice got to be infinitely small. But gamma is kind of, it's the continuum equivalent of the dynamics. Okay, so what's the, what kind of problem or PDE do you get when you take the limit of these action principles? Well, it's sort of an obstacle problem. It's just, so the first condition, V is or this unknown function, and it has to be pointwise bigger than this obstacle minus G. And minus G is something simple. It's the green function for RD, okay? So that kind of encodes the initial condition of starting with n chips at the origin. And that's very nice, and it's rotationally symmetric. So we understand it. I mean, we have a formula for G. So the other part is the hard part. It's saying that the Hessian of V plus G has to belong to this, this set gamma. And that's the only thing in this problem that's not rotationally symmetric. Now, there's some technicalities with how you interpret this minimization problem. On the one hand, you want to minimize over a very large family of functions. That's helpful. But on the other hand, so you want to minimize over all continuous functions. But then you have to say what you mean by the Hessian, because you can't just take second derivatives or even first derivatives in a classical sense. And so you do this in the sense of viscosity, which, I mean, the basic idea is that if you want to make sense of what's the derivative of your function at a particular point, maybe think of the absolute value function or something. So, you might pick a bad point where your function just doesn't have a classical derivative. So what you do is you take a smooth function and you just touch the function you're interested in at that one point. You keep your smooth function below, what is my name? V, or U. Okay. So you keep your smooth function below U, and you just touch it at the one point you're interested in, and then you put all your derivatives on the smooth function. And so saying that the Hessian of U, which U might not be smooth, okay? But saying that the Hessian of U belongs to gamma, what it means is that for any touching smooth function phi, it touches it at a point x, and lies below, the Hessian of the smooth function belongs to gamma. Kind of transfer all your derivatives to this smooth touching thing. Right, so you don't get to choose your favorite phi. This has to be true for all phi. So the statement d squared u belongs to gamma means for all points x and for all smooth phi that touch from below at x, Hessian of phi belongs to gamma. Right, that's right. So we'll see a picture of gamma in a moment, but gamma is a big downward closed set of matrices. So for different phi, you would get different elements of gamma. Okay. So there's this whole theory of viscosity solutions, and that was, that was the key ingredient, coming from Charlie Smart that kind of broke this problem open. And, Charlie and a few of his PDE colleagues understand this theory really well, and the rest of us are kind of learning enough of it that we can try to follow what they're saying. But if you want a short route to making progress in this area, then learn viscosity solution theory. So it's going to be very useful. Okay, so what is this gamma? Let me give you just a, unmotivated but complete definition of it first, and then, we can see how where the definition came from. So just to define gamma, it's a set of d by d real symmetric matrices for which there's a vector b and an integer valued function v that satisfies some constraints. So the constraints are this familiar upper bound on Laplacian of v and a lower bound on v itself. So the lower bound is a quadratic, and the quadratic comes from the matrix A. Right? So the recipe is for each matrix A, that determines a quadratic function on ZD, this x dot ax. And then you're looking for an integer valued function that lies above that quadratic and yet doesn't bend upward too fast. Right? And for some matrices A, this V exists, and for other matrices A, it doesn't exist. And gamma is just a set of A's for which such a V exists. Now, when you define it, like in the top, it's totally unclear. Like, how would you test if I give you a matrix, like the identity matrix or something? How would you even test if it belongs to gamma? But if you look at it for a while, you see it starts to look plausibly related to a sandpile because, well, to make things a little easier, let's just fix the B, okay? Say I even told you which B you're supposed to use, and I want you to check whether the V exists. So what do? Well, you have to be integer valued, and you have to be bigger than this quadratic. So the smallest function you could be is just the ceiling of this, of the quadratic. Right? So I'll stress A is not an integer matrix. So if I plug in an integer vector x, I'll get some real number here, right? So I might need to round it up to the nearest integer. And then I check, did I violate the Laplacian constraint? Well, if I did, it means my Laplacian somewhere in ZD has to be bigger than or equal to 2D, right? And what should I do in that case? Well, the only way to decrease the Laplacian is to increase the value of V by 1 at that point x. Because any other change I make, right, I can't decrease V. I already started with the smallest V. And if I increase V elsewhere, I'm only going to make this Laplacian even bigger. So, and what happens when you increase V by 1? Well, it's exactly like a toppling, right? So I'm going to decrease the Laplacian by 2D, and I'm going to increase the Laplacian of the neighbors by 1. So, okay, so once you phrase it this way, you see that A belongs to gamma if and only if a certain sandpile stabilizes, namely the Laplacian of the ceiling of this quadratic. And now this at least gives you an algorithm to check. If I give you a rational matrix A and a rational vector B, then this sandpile, SAB, it's going to be periodic. And so I can check whether it stabilizes just by doing a calculation on a finite torus, right? So either it will stabilize on that torus, or I'll topple so much that every side toppled at least once, and then I know it will topple forever. So at the beginning, we had no idea what gamma would look like, and this is actually how we started making pictures of gamma. So here's the coordinates I'm going to use for my picture. So take advantage of one feature of gamma, which is that it's downward closed in the matrix order. So if you have two matrices whose difference is positive semi-definite, and the bigger one, B, belongs to gamma, then A has to belong to gamma. So that means one way to think of gamma is it's the region below the graph of a certain function, lowercase gamma, and that function lives on the plane of traceless 2 by 2 symmetric real matrices. So I'm going now to dimension 2 for the simple reason that that's the dimension where we, with a lot of effort, can prove an exact description of gamma. So it's enough to describe this function little gamma. So it's a function of two coordinates, A and B, and there, A is the matrix +1, -1 on the diagonal, and B is the matrix 1 and 1 on the off diagonal. Okay, so after running this algorithm, we get a picture. This is a picture of the graph of this function, little gamma. And I still remember being in the audience at MIT when Charlie Smart was coming to give a talk, and he just had the very first pictures of gamma, and so he was showing some low-resolution version of this picture, and we were getting very excited in the audience. There's obviously something cool going on here, and I remember saying. Something like, okay, but these aren't geometric cones, like as if it's just obvious that, well, okay, they're kind of vaguely cone-shaped, but not going to be like perfect circular cones. And Charlie was like, no, they are geometric cones. So, so these are perfect circular cones. Alan, were you there at that talk? No, okay. Anyway. So, this is what the picture looks like from the, kind of the bottom slice. So if you slice through the bases of all the cones, they all end up being tangent on a single plane. And then it looks like this. And the stuff in purple those are the matrices that, where this function, little gamma, takes its minimum. It takes its minimum on this set, which you recognize as Apollonian circle packing. So it's a kind of famous picture that ends up on the cover of math journals and so on. And fortunately for us, this thing has been studied for a long time, so a lot is known about it. So the way you make this picture, before, if you weren't getting it in some weird accidental way from a sandpile, the way you would make it is you start with these vertical lines in the plane. They're separated at width 2, and then you tile each vertical strip with radius 1 circles, and then you iteratively place circles in the gaps so that each circle you place is tangent to the 3 surrounding circles. So like this guy is tangent to the 2 radius 1 circles and the line, and like this guy is tangent to these 3, and so on. Okay, so let me try to give you a little sense of why you might get cones just by doing one particular cross-section. So it'll be the cross-section containing the identity. So that turns out to be a point on the boundary of one of the on the boundary of the circle packing, and so from the identity you can either increase the so we're going to move in the direction of this this matrix that's -1, +1 on the diagonal. And when you do that, you get to the peak of one of the big cones. So let's see, why, in terms of sandpiles, why does that make sense? So the identity corresponds to the quadratic x1 squared plus x2 squared. And divided by 2. So there's a half in the definition of gamma. So the half gives you trouble. You don't like the function x1 squared plus x2 squared over 2 because it's not integer valued. So you add a linear term to make it integer valued. So that's what you see at the top. And then this has a nice simple discrete Laplacian, which is just all 2's. And all 2's is nice and stable, so you're happy. So that tells you that the identity matrix belongs to gamma. So this is a V that witnesses that it belongs to gamma. And now let's try to increase a little bit the coefficient of x2 squared. Right? If you do that, what happens to the discrete Laplacian is you end up adding extra stripes. So you end up getting stripes of 3s. And the bigger epsilon is, the more stripes you get, and eventually, you fill the whole thing up with stripes, and you've increased the coefficient of x2 squared from 1/2 to 1, and now you're at the maximal stable configuration, all 3s. So that's the peak of the big cone. And instead of that, you could increase the x1 squared coordinate, and that corresponds to adding vertical stripes. But if you try to increase both coordinates at once, so you add epsilon x1 squared and epsilon x2 squared, then you get horizontal and vertical stripes. And that's trouble, potentially, because here's a 4, which is unstable. Now, unstable doesn't spell doom, right? It might be that we can stabilize this sandpile, but in fact, no. So this guy, well, if you topple the 4, then the entire horizontal strip of 3s is going to topple, and the entire vertical strip of 3s is going to topple, and then you go outwards, and everything topples at least once. So this guy doesn't stabilize, and hence the identity, although it's in gamma, it's right on the boundary of gamma. So if you go straight up in the picture, then you'll go outside of gamma. So the picture is the identity is here at the, and you can crawl up this cone by adding vertical stripes, and you could crawl up this cone by adding horizontal stripes. If you try to do both, you're going in this direction. You immediately at gamma because you no longer stabilize. Okay, and then each other cone corresponds to some other V, and when you take the Laplacian of that V, you see a periodic pattern, and not just any old periodic pattern. You see the pattern that the patterns that actually arise in the sandpile. So it's kind of clear at this point what the theorem should be, that gamma is the set of all matrices B that are in the matrix order are less than or equal to these special peak matrices AC, as C runs over all the circles in the packing. So for each circle C, there's a peak matrix AC that lives right at the tip of that cone, and all the other matrices in gamma are the ones less than or equal to those. Well, having the explicit structure of the circle packing, it's kind of it's a blessing and a curse. So it's a blessing because you have a lot to work with, but it's a curse because it's so specific. So, with a lot of sweat, we were able to prove this exact description of gamma using a lot of special stuff about circle packings, which I'll tell you some of that special stuff in a moment. But it would also be nice to have like a general purpose machine that instead of a square lattice, if you wanted to do triangular lattice or some other periodic planar graph or some higher dimensional lattice, it would be nice to have a general machine that would tell you how to compute the peaks of the gamma of that lattice. And so far, our method for Z2 doesn't give much insight into how you would do it in general, because it kind of relied on seeing the answer in advance and using all the special structure of that answer. So, on the other hand, the advantage of the construction is it's explicit. So for each circle C, we actually construct a function VC that obeys the inequalities. And that function gives you a periodic pattern associated to each circle. So here are some examples. Okay, so what's the recursive structure of the packing? So this goes back to Descartes in 1643. He wrote a letter to the Princess of Bohemia where he was telling her about one of his discoveries. And that in those days, that's how you impressed the ladies. So his discovery, well, in modern language, looks like this equation: C0 equals twice the sum of C1, C2, C3 minus C4. you won't see that equation in Descartes' letter. You'll see some like 6-degree polynomials, and it looks very, well, I would say ugly, but I guess I shouldn't really be insulting, you know, dead philosophers. But anyway, so I mean, I wouldn't have discovered it at all, right? So, so what does it say in modern language? It says, you've got this circle here, okay? You want to know, well, first, what Descartes wanted to know is, what's the radius of this circle? And he suppose I know the radii of the 3 green circles that are mutually tangent, and those 3 green circles determine 2 red circles with the property that the red circles are tangent to all 3 of the green ones. So this red one on the inside is tangent to the 3 greens, but there's also another one on the outside that's tangent to the 3 greens. We call that the grandparent. The big red one is the grandparent of the little red one. So suppose you know the curvatures of everybody except for the little one. Curvature is 1 over the radius, and it's useful to work with curvatures because curvatures are going to be integers. So Descartes' relation says the curvature of the little red guy is twice the sum of the curvatures of the 3 green guys minus the curvature of the big red guy. So that's pretty cool. I mean, now you might also want to know, though, not just what the curvature is, but where that circle is located, like where its center is. And this always amazes me that it took 300 and something years before Lagarius, Mallows, and Wilkes discovered and proved that the centers obey the same linear relation, provided you first scale them by the curvatures. So I'm going to think of a circle, right? A circle has 3 degrees of freedom in the plane. It has a center, which is 2 degrees, and then it has a radius, right? So the coordinates that are magical that you want to use here are the curvature times the center. So that's, you know, think of the curvature as a real number, and the curvature times the center as a complex number. And if you parameterize your circles that way, then, you know, the same linear relation holds for for all 3 coordinates. So you can go and label all the circles in the packing in their curvature coordinates. And I mean, number theorists love this because everything is integers and Gaussian integers, and they've asked all kinds of questions like which integers appear, and, you know, what's the density of the integers that don't appear, and you know, you can go wild with it. But for us, these coordinates are just tools to use to understand the sandpile. So, okay, we know that the curvatures and the centers obey this relation, and what we want to do is associate a periodic pattern of sand to each circle. And so, after staring at these patterns for a long time, and Wes Pegton is, you know, on his computer, he opens up like a paint program and is kind of taking these, you know, fundamental tiles of the periodic patterns and like cutting them up and, you know, moving them all around and trying to glue them together. And so you start to realize what has to be happening is, if you want to build the fundamental tile of your new circle from the tiles of the 3 parent circles and the tile of the grandparent circle, what you should do is, well, you should look at this relation and say, I want to take 2 copies of each of the 3 parent tiles, and then I want to somehow subtract out a copy of the grandparent tile. And how do you subtract something out? Well, one way to do it is to overlap 2 of the other tiles on a copy of the grandparent tile. So that's what's going on here. So the grandparent is this guy, and you see it appearing in the middle of the new tile we're constructing. And it appears on, there are 2 copies of this parent tile here that get superimposed and happen to match in the middle on a copy of the grandparent. And then here you've got copies of the other 2 parents and copies of the other 2 parents. So you see in each instance, you know, how it works, okay? And it looks promising, but on the other hand, these tiles, the projector is kind of blurred, so I don't know how easy it is to see, but the tiles don't have any convexity or anything that would help you out. So like they have all these little indentations and stuff. So it seems like a nightmare to try to carry this construction out, because you would have to prove that the tiles fit together exactly without overlapping and without leaving any holes. You have to be ambitious to even try to do something as foolish as carry this construction out. So I mentioned these difficulties to Catherine Stang, an old friend and a number theorist, and that got her thinking about circle packings, and eventually she wrote this great paper called The Central Apollonian Circle Packing, which is a riff on Conway's central quadratic form. And her ideas kind of helped us actually carry out this construction. So I can't really give you the detail, but I'll give you the flavor. The flavor is that you need to say how the tiles are offset relative to each other when you're gluing them together. And that's encoded by these offset vectors. So each pair of tangent circles in the packing that's associated in an offset vector v. And you can define these v's by a recurrence. So these first two equations are enough to recursively define all the v's. And then you go and check by induction that the v's also obey a whole bunch of other useful identities. Like, for example, this red identity. So I like this one. So this one is saying, if you look at the difference between the centers of two tangents, the location of the center of one minus center of the other. So that's some complex number, and it's not a Gaussian integer, but if you multiply by the product of the curvatures of the two circles, then it's obviously a Gaussian integer because, well, everything is an integer by induction. But magically, it turns out to be the square of a Gaussian integer. So you get all these just seeming coincidences like this. Okay, and so you have these offset vectors that tell you where the tiles are supposed to go relative to each other, and then you arrange them, and then you hope that a bunch of things that you think are true are actually going to come true, which is that two copies of the biggest tiles overlap on a copy of the grandparent tile, and when you put everything where it's supposed to go, there are no holes and there are no overlaps. And so we were in the kind of following situation, which maybe arises in this kind of dilemma might be useful in other situations where it was really hard to check disjointness. Like checking that two tiles don't overlap was daunting. But on the other hand, we could easily verify many adjacencies between tiles. So we wanted some recipe for how can you prove that a bunch of tiles actually are a tiling of the plane if you can easily verify adjacencies but not disjointness. And well, if you pile on enough conditions, then you can avoid ever having to check that anything's disjoint. So I won't go through the conditions, but it's good to know that it can be done. And then one extra surprising thing that happens when you do this recursive construction is that the tiles, the construction is 180 degrees symmetric, so it's obvious that the tiles themselves will have that symmetry, but they turn out to have 90-degree rotational symmetry as well, even though the construction doesn't. And so the one thing you get out of this construction is a family of primitive periodic hexagonal tilings of the plane by identical 90-degree symmetric tiles. And it'd be interesting to know if these are all of them. So for each circle in the circle packing, there's a tiling with the properties. They're kind of hard properties because hexagonal means you have to touch 6 neighboring tiles, but each tile has to be 90-degree symmetric. Kind of a weird combination of symmetries. So maybe these are all such tilings, and that would be fun to prove if it's true. Okay, and then more in the realm of topic of this workshop, this is a tip of the iceberg, right? So for one lattice, the square lattice in Z2, for one particular model, the Abelian sandpile, we have this exact description of gamma, which is telling you like which features of the square lattice are still relevant in the scaling limit. And you'd like to be able to do this in higher dimensions. So what's gamma of Z3? I think that's like a good PhD thesis. It's not going to be easy. It's a high-dimensional set, right? It lives in 3x3 symmetric real matrices. So, but you can get data, and you can, cut various slices of it, and there'll be lots of conjectures that you can make, and then you can try to prove them. So it's going to be something cool. And in general, for any periodic graph embedded in RD, there's an associated gamma of that graph. And it would be nice to have an algorithm that computes its maximal elements. Here's a picture of gamma of the triangular lattice. So you can see it has some similarities with the Apollonian packing, but it has some differences too. Like Apollonian packing had the nice feature that the minima of this function, little gamma, were all simultaneously attained on a single plane. So you had these cones, but like there was one plane where they were all tangent. And in this triangular lattice picture, that's no longer the case. So the cones kind of intersect in space. They don't all come together in one plane. Okay, so this is the paper that has the full construction, and it's probably, in a sense, you don't want to read it because it will tell you how to do the construction in detail in the square lattice, but then at least it didn't give us any insight how to do it in more generality. So, okay, so I'll stop here and thank you.
Yeah, we have some time for questions and comments and speculations and discussions.
For the triangular lattice, yeah, so it does seem to be a union of downward closed cones, and right, so at each, the tip of each cone there's a matrix, and it seems like that matrix has rational entries. So that would be a very interesting thing to prove, by the way. That not sure what conditions you would need, but there should be some conditions on your periodic graph that would guarantee that all the peak matrices are rational, and we seem to see rationals, but I'm not sure why. So. Yeah. Yeah, the color is the height. So this is the AB plane of traceless 2x2 real symmetric matrices, and then so you're looking at the graph, like a heat map of the graph of gamma. So here's a cone coming out of that plane, and red is the highest color, so this is a big cone, and blue is like some middle color, so there's like a little cone coming out here, and purple is the lowest color. So these points, I mean, there are little cones here that you can't see at this resolution, but these points are low. You mean like these? Yeah, so they're all circular cones. It's just they come together in a funny way, and we don't know where their peaks are. So it's all about finding the locations of the peaks, because once you have a matrix in gamma, everything below it in the matrix order is in gamma, and geometrically that's just the condition that the whole cone below it is in gamma.
Do you have some simulations in higher dimensions?
A little bit. Yeah. So I can try to find one to show you, but let me describe it first. So one thing that intrigues me about higher dimensions is there's a kind of dimensional reduction. So if you take a three-dimensional sandpile and then cut a two-dimensional slice of it through the origin, then it looks in certain ways like a two-dimensional sandpile. Basically, so let me be more specific. So say I take n chips at the origin in Z3 and I stabilize. Right? So I'll get this three-dimensional thing, which, it has a limit shape. We are pretty sure the limit shape is not a Euclidean ball. And it has patterns inside, and you can kind of see the patterns. One way to see them is just slice them, right? And if you slice it, then, well, you'll have a picture with 6 colors, because the heights can be 0, 1, 2, 3, 4, 5. Right? Now, even though the picture has more colors, it turns out that the colors, 2 of the colors don't appear except near the origin. So only, I think 0 and 1 don't occur far from the origin, if I remember right. So kind of, if you excise a little ball around the origin, which has all 6 colors, then you'll get a 4-color picture. And that 4-color picture looks very much like just a two-dimensional sandpile started at the origin, but with some different number of chips. So I think I talked about this phenomenon once with Deepak years ago, and he had a good explanation of it, which is, when you stabilize the 3D thing, well, certain regions are going to have, like, for example, there's these regions where everything ends up with exactly 5 chips. And so you'll get these long columns which are just constant in height. And so those columns have the same dynamics as a two-dimensional file. So you can, in that sense, you could see the two-dimensional dynamics in certain parts of the 3D picture, but still surprising somehow that the pictures would match so closely. So I even tuned the number of chips in 3D to the number of chips in 2D so that I could overlay the 2 pictures. And then near the origin, they're totally different. Even the number of colors is off. But then there's a region where they almost match pixel for pixel. So there's like some defects, but almost all the pixels match. And I mean, that's like a pretty strong resemblance. So I mean, there's so many things in this sandpile world that one could try to work on. It's a little bit hard to decide which problem is the most interesting.
Any other comments or questions? Right. If not, let's thank Lionel for this excellent set of lectures.